Okay, so welcome everyone. I'm here to do a little workshop about the car hacking stuff, and we will go to an initiation to the canvas and every technique we can use to read, write, get data from the canvas and play with the data going through the canvas. First of all, I don't know if every one of you had already downloaded all the material that you can use during this workshop. There is a virtual machine and the PDF you can access using the link displayed there, and you received it on your email. I do recommend using VirtualBox because there is some math on some ports. On the virtual machine, you will have a virtual car that you can get access to using a browser and using also a terminal. You can.
Hey, Philippe. Sorry to interrupt. Your volume is a little low. It just got a little distant somehow. If you're
okay, wait a minute. I'm getting much more sound. Okay, it must be better there.
Much better. Absolutely better.
Sorry. So for those who don't understand, so welcome to this workshop. As I said, if you didn't have done it yet, using this link, you can download the virtual machine and the PDF that we will be using during this whole workshop. It's on the VM, you have a virtual car and all the canutils commands to play with the virtual canvas available on the virtual car. But before getting into the canvas, we'll discuss a little bit about automotive security. If I ask you, what is a car? You will think first that a car is four wheels, steering wheels and a motor, as it has always been from decades to decades. But in the last years, we have seen many great improvements on the modern cars. For all the driving assistance. Now, when you drive your car, the car helps you driving with the anti-collision system, lane detection, all the braking assistance and stuff like that. You even have advanced intelligence with camera doing reconnaissance of the surrounding to detect cyclists or speed signals, stuff like that. You also have a great improvement to the connectivity. Now, all the car GPS receiver are connected to 4G or 5G networks, offer Bluetooth and Wi-Fi connectivity on them. Using those connectivity, it brings us some onboard services, allowing you to remote control your car using your smartphone to locate or get some diagnosis from the car or any discussion with the backend systems. And the most important thing is the autonomous driving that is getting more and more important. For your information, when we speak about autonomous driving, we all think about Tesla full self-driving, but on the 5 level of autonomous driving, Mercedes was the first to reach the level 3, which means the car was able to drive by itself on a specific road at a specific speed, and they did it on fall 2021. And how can we get such improvement available on our car? It's due to the ECU. The ECU are the electronic control units. There is many into a modern car. You can have between 80 to 100 ECU on a car. But if you look at what is an ECU, it could be very simplified. It's an ECU, it's just an embedded device. We read data from different sensors, and using this data, it will handle manage actuators. For example, if you have a rain sensor, it will detect rain, and then the ECU will trigger the wiper motors, so your phone glass will be clean from all the water. Okay, and then as the ECU has to exchange data between each other, so they are connected using different network, and so they can communicate between ECU, other device, or any backend. Okay. On the right of the PDF, you can see an example of telematic control units. And what you can find into an ECU is you can have one or several microcontroller or system on chip available. So yeah, could be very simple stuff or very advanced and complicated embedded device, depending on the task the ECU has to do. We may use it during this workshop, but it's very common in the automotive industry to give name to ECU using trigram or quadrograms. So I may speak about some kind of ECU. For example, if I tell you about the BCM, it will be the body control module. The body control module is a very important ECU into a car because it manages most of the body tasks, like the lock and unlock systems, all the light controls, stuff like that. You also have the powertrain control module could also be called the ECU for engine control units, depending on the manufacturer. All those names are manufacturer specific, so yeah. And I just told you minutes before about the TCU, which is telematic control units, and this ECU, which will be having connectivity with the external network or the backend system of the manufacturer and stuff like that. It's very, very good ECU from a security assessment point of view. Okay. And all those ECU communicate between each other. They do use different kind of networks depending on their needs. Okay. The most common one and the older one is the CAN, the Control Area Network. It's a very old network designed in late 1980 by Bosch. And it's a very reliable network. And it's still the most common one you will find on modern automotive for the connection between different ECU. And you will find on your car, on any other car you can play with, different kind of network depending on the bandwidth you need or the application you need. For example, for non-critical application like locking or unlocking the door, maybe the canvas will be too expensive to use, and the manufacturer will use a LIN, local interconnect network, which is a network working on only one wire. But for more advanced application like full self-driving and stuff like that, we will see, for example, automotive Ethernet, which is the 100 on 1000 based T1 network, which is an Ethernet-like network for car, or flex array system, or most which are a very expensive network, but offer a higher bandwidth than the standard CAN network. Okay, and all this network, all these ECU can be connected between each other using one or multiple internal network. Of the diagram, the schema here, the picture you will see there. Okay, and this increase into connectivity between all the ECUs, the technology used in all the ECU has a major effect on the modern car. It's now all the attack surface are very, very wide. So you have 10 or 20 years ago, the main attack surface you may find in a car will be through the OBD2 connector, which is the diagnostic connector, the one you find near your steering wheel. But now you are much more connectivity, much more attack surface, as illustrated there. So you may find on your infotainment unit, you have USB connectivity. This is this unit which offers you Wi-Fi or Bluetooth connectivity. Using your telematic control units, you will have a 4G, 5G connection. As we want more green car, you will have a connection between your electric car to the grid using PLC, power-line communication. So if you manage to get access to the grid, you can communicate to any connected car, which is charging and stuff like that. There is also new incoming technology, which are not yet clearly defined, like V2V, V2G, vehicle to vehicle, vehicle to ground, which means in the future, in the very, very near future, all the car will be able to discuss with each other. And for example, if a crash happens, an accident, or a car detects a hazard, it will send a message on these networks, and then all the surrounding car will get it, and your navigation system, for example, will calculate a new course to avoid the danger. Yes, you also have the computer vision, as I said. Assisted driving. For the assisted driving, you have no camera which are looking for your environment. And for example, there was some attack where people just cast image on the floor, on the ground, on the road, and then the car believes that something that wasn't there is present. You also have radio communication for the TPMS, which is a sensor on each tire for which tells you if you have flat tires or not. And also you have mobile connectivity with RFID and UHF using your key fob or your cell phone to lock and unlock your car or do stuff to, for example, start your HVAC before getting into your car. So it will be cooler. Okay, so as we can now see, that there is a very, very huge amount of attack surface available on motor car. And the fact is, as all those new stuff were put into new car, the security was not the main concern of automotive manufacturer. And the milestone about cyber security in automotive was 2015 with the famous hack of Chris Miller and Wallachek, when they did manage to get a full control of a car over internet. The fact is, on this car, it was an old Jeep. It was a Jeep, sorry, not so old. The infotainment units could do some firmware upgrade, but there was services available over the internet, and using these services, they managed to send a fake update, and then with this fake update, they were able to communicate on the canvas of the vehicle, and this canvas was not segregated. So that means that using the connectivity, the infotainment system was connected to all the main canvases of the car. So they were able to activate the brake, to move the steering wheel, to lock on the door. So stuff that must not happen on a working car. And this is a milestone, because from this event, manufacturer get aware that they have to secure the car. And also, we now have a new regulation from 2021, which now, for example, firmware upgrade is no mandatory in the future car that have to be produced. Okay, and also now on the modern design of a car, you will find is using a gateway. So all the different network will be segregated. So for example, if an attacker managed to find a flaw into telematic control unit and have access to this control units, it will not be able to get access to other network of the car, because that's the role of the gateway. The gateway is here to protect the different parts of the networks and ensure that no unauthorized access are available on the car.
Hey, Philippe.
Yes.
There's a question on the Zoom chat.
Yes.
Is OBD3 connected to online, and can we use those for attacks?
OBD2, you mean?
Yes.
Yeah, the OBD2 is available for attacks, but to have access to the OBD2 plug, you have to be inside the vehicle. So, in fact, this is not the kind of it's not the main concern for the automotive manufacturer, because it means you have access to the car, and the attacks or the damage you can do are very local. You can just make some action on a specific car. That's why, but if the network is well designed, the gateway will be between every kind of access. So it will protect from the TCU, it will protect also the OBD2 port and anything. But yeah, local attack are not the main concern of automotive manufacturer, because yes, they are local. Okay, it's like if you can have access to your phone and root your phone, yes, you have access to a phone, but you don't have access to any phones that are connected to the network. That's I hope I have answered the question. Okay. So what about the canvas? So as I said, the canvas is the main network you will find on automotive, on a car. It will still be the most important one, because it's a very cheap bus, and it's very designed to be used in automotive. For all the new, modern, and much more high bandwidth network like automotive Ethernet or FlexRay, which allow advanced application. There will not be used for all the communication between ECU, because they are very, very expensive. And you don't want to, people don't want to buy their car $1,000 more than the usual price just because they have very high-end network in it, if it's still working with the CAN bus. So they will use CAN bus. So how the CAN bus work and why do we need a CAN bus? So as we said, to have a proper function of our car, we need to connect all our ECUs between each other. So they will share the data they read, and they will share the data of the state of the actuator they controls. The first idea could be to connect all these ECU between each other using a dedicated cable, okay, like a point-to-point network. But if we do so, the fact is when we had to add a new ECU, we will add to this ECU the total number of ECU minus one new links. So the more wiring we have into a car, the more cost it will be. It has it will have to be produced, and also all the cable, all the wire, all the copper, on a car add weight, and if you add weight on car, you reduce its autonomy, or it have to consume more. And now people want a vehicle with the lower consumption at all on the higher autonomy. Okay, so this kind of design is not good at all for the automotive industry. And so that's why the Bosch designed in 1986 the CAN bus. The idea is, as its name said, it's a bus. So all the ECU will be connected to the same bus. So you will only use two wires to connect all your ECU. This bus is now mandatory in Europe since 2001 and 2008 in the US. And you will find this bus in many other applications like industrial system, ICS, medical device, train, planes, even in tanks. Yes, yeah, it's a very cheap and reliable network. So it's something you may find easily on any kind of assessment you may have. The CAN bus is also defined by ISO 11898, if you want to look at the documentation. And as it's an old protocol, it has some evolution, like CAN-AD on CAN-XL. This evolution allows the CAN bus to be to have more speed and send much more data than the older and the legacy one. Okay. How the CAN bus work? So, as I said, you have all the ECU that are connected to the same bus. So here we have 6 ECU, a power control module, a telematic control module, driver door module, the ABS, body control module, and the instrument cluster. Okay. And if the CAN bus work using a broadcast protocol, so anytime a ECU send a message, all the connected ECU on this bus will get the message. Okay, so for example, the PCM, the power control module, send a message on the CAN bus. As it is a broadcast protocol, all other ECU will receive it. And that's something we don't really want because we don't want to overload all our ECU. So using a specific aspect of the CAN bus, which is the arbitration ID, the ECU will filter the data they receive by looking at this information, the arbitration ID, and if this is an ID they want to use, they will keep and process the message. Otherwise they will drop it. Okay. The arbitration ID has also another utility. It's what if we have two ECU that wants to send a message at the same time. Okay. And the arbitration ID will be used to avoid any collision. So the lower the ID, the higher priority the message will have. So for example, if at the same time we have the power control module and the driver door module, which want to send a message, as a power control module have a lower ID because it's X123 instead of X321, the driver door module will stop sending its message, wait for the power control module to send its message, and once the bus is available, it will try to send a new message. Okay, so when a ECU is writing on the CAN bus, it's also reading on the CAN bus at the same time to during the arbitration ID phase to ensure that there is no collision at all. Okay, so that's what happened. So as they want to write all the ECU, the two ECU want to write a message at the same time, the higher ID is dropped. Okay. On the canvas, you have four kinds of can frame, and the two more common and the two more used will be the data frame and the error frame. The remote frame and overload frame are older kind of frame. Remember, the canvas was designed in 1986, and at the time, the microcontroller used are not as powerful as they are now. They have less memory, less processor, less speed. So for the remote frame and overload frame allows our frame that were designed to say, okay, I miss a message, send it back, or wait a minute to send new message because my memory is over, for example. If we look at how can frame looks like, that if we want to send 1 byte of data, and I forget to say that on the legacy canvas, the data are limited to 8 bytes. So can frame can handle up to 8 bytes. Okay. So we have our arbitration ID, which could be 11 bits, or 29 bits for the extended ID mode. And then we have a first control. The canvas is designed to be reliable. So it's designed to avoid any kind of error, collision, and stuff like that. Then we have our 1 byte of data, and it can be up to 8 bytes of data. Then we have a checksum, an acknowledgement part. So each ECU will acknowledge that they have received the message. So if there is an issue during the reception of a message, the sender will know it, and it will manage an error system. And we have an end frame. So we can see that when we have to send 1 byte of data using a can frame, most of the bits will be used for the error verification and not to handle the data. Another kind of error management, which is used into the can frame, is the bit stuffing. So, for example, if I have five times the same bits, which have to be same, the can frame will be increased by 1 bit to send the opposite bit. Okay, so for example, you will never have 6 consecutive 0 or 6 consecutive 1 in a can frame. It's not possible at all. It means there is an error. Okay, so we see that it's designed to be reliable and to ensure that all the messages are correctly sent and received. We also have another kind of frame, which is the error frame. And to send an error frame, it's just that we send 6 times the same kind of bits. So it's again the recessive model, not recessive, sorry, the bit stuffing model we just saw earlier. And error frame are very, very important because when there is counter, each ECU will manage counter. And when the transmitter counter, that means when a ECU send a message and detect or receive an error, it will increase its transmit error counter. And when its transmit error counter is over 255, it will switch to bus off. That means the ECU will disconnect from the bus, stop sending and reading data from the canvas, and wait for a specific time to reset, to replay with the bus. And using this kind of error frame or this kind of system is very easy to create some denial of service on a canvas. We'll talk about this a little bit later. So physically, how the canvas works. The canvas just use 2 wires to connect all the UC. You can see that you have 2 wires, the can high and can low wire, and the bus is terminated on each part by a 120 ohm termination. It's very important to prevent signal reflection. If you want to buy an ECU on the scrapyard and start playing with it, if you forget to add the termination, you will have issues when you want to read or write on the canvas. It's very important to check for this termination. And we have there, you can see that each ECU is connected directly to the bus using the can high, can low wire. The canvas use what we call a differential signaling. So it means that depending on the voltage on each line and the difference, it will be a 0 or it will be a 1. By default, the dominant state of the canvas is a 0, so that the CAN I wire will be at approximately 3.5 volts and the CAN wire will be at 1.5 volts. And when we want to send a 1, which is the recessive state, we will add 1 volt to the CAN low wire and drop 1 volt from the CAN I wire. So they will have the same value, the same voltage as we see there. Okay, so it's very effective to detect any problem. And as we can see there, if you have any teeny difference in the voltage, you can still send a good data that will be received and by other ECU. Even if you have a problem with the ground, they don't share the same ground or stuff like that. And then about the canvas, a canvas is defined by its speed. There is different speed that are designed to be used for the canvas. And the most common one you will find is 500 kilobytes per second. For non-critical buses, we will use a lower speed, but most of the time, if you have to look for an ECU, start with 500 kilobytes, and you may find good results. As I said, we also have newer kind of canvas like the CAN FG or CAN XL, and we can get over the limitation of 1 megabytes per second with 5 megabytes per second or 10 bits per second. Yeah, for the CAN itself. The cool thing with the CAN FD is it's for the arbitration phase, it's backward compatible with the classic CAN. So a CAN FD will be able to read data from legacy CAN bus, but the opposite is not possible. So if a CAN FD transceiver is waiting to a standard CAN transceiver, the standard CAN transceiver will not be able to read a CAN FD frame to throw an error. If you want to locate the canvas, a canvas into your car, the first things to start with is the OBD2 port. This port. You will have one on your car. It's mandatory. And on the pin 6 and 15 and 14, okay, you will have CAN high, CAN low, and just put an ohmmeter on it, and you will find a 60 ohm impedance. Because we have two 120 ohm resistance in parallel. I also look for an average voltage of 2.5 volts. Okay. I also forget to say that to avoid interference, the canvas is always a twisted pair, and there is not so many twisted pair on a car. You will find twisted pair for radio, for anything that is frequency related, for example, the transceiver, for the transponder chip of your key fob and stuff like that. But if you have a twisted pair, it could be a canvas. Just look for the 60 ohm impedance, and if you find it, you know it's a canvas. Okay. About the OBD2 plug, as I said, here are the normally all the OBD2 plug has to be set. All the 3 pin are manufactured to do whatever they want, but on pin 6 and 14 you will have the CAN high and CAN low to connect it to the power control module, because it's mandatory for diagnostic. And you will also have on pin 16, permanent 12 volts, and on pin 4 and 5, the ground. So if you have to connect any device to your car, any testing device, you know that you will find voltage on the canvas.
Hey, Philippe, sorry to interrupt. There's a question in the QA panel, like what is the difference between an active versus a passive error in a car?
Yeah, the fact is, by default, an ECU will send an active error. But when this error counter reaches a certain level, I mean quick, okay? If an ECU has two error counter, a transmit error counter and received error counter. If he received an error counter when he was just listening to the canvas, it's the REC, which will be increased. If it received an error when it's transmitting, it's the TEC, which will be increased. And to avoid, because an active error frame increase all the error. If the TEC or REC get over 127, it will switch from active to passive error. So it's avoid to have sort of loop of error, and so all the ECU switch to both of that. That's all. Yeah. Most of the time, we can see that the passive error just it's a standard signaling on the canvas, so it's other design. Yeah, that's the concept. It's way to send an error. Yeah. Okay. I have understand the question. Okay. Before getting into our virtual car and playing with the canvas, just a safety warning. If you want to play with the car, your car or any other car, first of all, get access to the documentation of your car to see how things are connected to. Know where the power outputs are and stuff like that. Use appropriate tools so otherwise you can break your car. If you remove parts of your car and you see yellow connectors, be aware, because those connectors are most of the time related to all the safety system and the airbag, and doing weird stuff with it could trigger the airbag. So be aware. Okay, it's very important. Just a reminder. Airbags are pyrotechnic systems, and if you do it on your face, it's not very pleasant to, So, well, you can play with your car, but beware of the yellow pictures. And the bigger the wire, the more amps you will have on them. So avoid doing any shorts, because, you can have not so good surprise with us. If you want to play with the canvas, you will need a transceiver, CAN adapter that is able to read the canvas and convert the data that will be readable by your computer. If you look for the simplest CAN adapter, it will be the ELM327, which is a Bluetooth adapter that you may find for very basic diagnostic stuff. But avoid using such items because it's very, very limited. You can find also a CAN transceiver like TGA 1050. You can connect with Arduino or Raspberry Pi to play with your canvas. If you are using Linux natively, the CAN interface is native with Linux, and you can use some low whistle protocol on SLCAN device to connect to a canvas and play with it. Or the better is second CAN because it's much more better and much more reliable. And if you have access to professional tools, those kind of tools will manage different kind of network on one package. So it's way better when you have to look for different CAN bus at the same time, or play with other kind of network like LIN or alternative Ethernet. Okay, so as I said, on Linux, you can create a virtual canvas using the standard IP command. This bus is already available on your virtual machine. If you want to create a virtual canvas on any Linux distribution, just type these two commands, and it's just the first one, declare the vcan 0 vcan bus, and then we have to set it up, and it will be okay. The virtual canvas is able to handle CAN-FD data, so it can handle up to 64 bytes of data instead of the standard 8 of the standard canvas. It's also very common to name the canvas you would use regarding the device you are using. So if you are using a virtual CAN adapter, you will call your canvas vcan and the number of your canvas. For standard CAN, it will be CAN and the number of your canvas. And for socket serial layer, scan over serial SLCAN stuff, it's common to name your bus SLCAN 01 and so on. There is a good library, which is CanUtils, which have many applications to play with the canvas, which allows you to read and write on the canvas. The main command is candump. Candump is very simple. It will read the canvas and display all the data going through the canvas. If you have started the virtual machine that is available for this workshop, you can connect to the virtual machine using port 5022, okay, on your localhost with login user. Okay. The password is password, okay, and you're in. And for example, if I tap candump, the name of my bus, which is vcan0, all the data will be displayed on the terminal. So on the first column, I will have the name of my bus. On the second one, I will have the arbitration ID. So remember, the lower, the higher priority my message will have. Then it shows me the length of the can frame. So for example, there I have an 8-byte message, and I will find the 8 bytes displayed there. There is many options that are available with Candump. And for example, if I type the option -A, just -A, it will display the ASCII value of the byte of the can frame. Okay. I can also use the -X option to know if this is data I received or I sent. So it's very useful when we want to know where the data comes from, if it's from my computer or from any other ECU on the network. So very basic. Okay. You can still use the standard -H option to see all the available arguments options for Candump. Okay. But if on our virtual machine, the simulation is very easy because there is very few messages that are broadcasted. On a real vehicle, you will have plenty of message. And I forget to say that CAN data are sent periodically. So for example, on the ABS, because it's the speed of the vehicle, because it's the ABS, we read the speed of the speed of rotation of each wheel and we compute the speed of the vehicle. So the ABS will send the speed of the vehicle every X milliseconds. Okay, so when you have a CAN frame, the CAN frame will be sent at a specific interval. It's designed by the manufacturer. And on a real car, you will have plenty of CAN frame within a second. So just using Candump to play with the canvas is just impossible because you will have too many messages. There is another option which is very useful with Candump, is that you can filter the data you want to read. So for example, there, I want to filter all the data using arbitration ID X123 and with a bit mask. So as on the standard canvas, the arbitration ID is limited to 11 bits, it means that the maximum value of the arbitration ID will be X7FF. So for example, as this one is a bit mask, it means I want only to display all the arbitration ID, all the message using arbitration ID 123. There I add another filtering, and I only want to display all the message that start with 03 because I do my bitmask with this first part, and as the last part of my bitmask is 0, it means it's a wheel card. I will display any arbitration ID going from X03 to X03F. Okay, as we see there on our output. Okay, so it's very useful because when you want just to follow 1 or 2 or 3 arbitration ID using Candump and the filtering option allows you to reduce the amount of data that are displayed by Candump. Before getting deeper into this workshop, you also have, for the virtual car, you also have a graphic interface using a browser. So if you connect to this IP address, you will have the control of your virtual car. Using the commands like there, you can, for example, accelerate, decelerate, open and unlock some doors. And all those commands will have effects on the canvas, and we will use those commands to play with different commands from CAN-utils. Okay. So just a reminder, you have the IP there to get into the graphical interface, and if you want to connect to the terminal using SSH, those are the parameters you have to set. So remember, login is user and password is password. So first of hands-on on this workshop is just reading the canvas. So if you have installed and launched the virtual machine using CANDEM, just read the vCAN 0 bus. I forget to show you. Using IPA on my virtual machine, I see that I have my vCAN 0 network interface up and running, and it's a CAN type of interface. Okay. So, as we saw, if I type vCAN 0, CANDEM vCAN 0, I will get the output of my canvas. Then I want to filter to only display all the arbitration ID, all the message with arbitration ID X1E0. It's very easy using CANDEM because I just have to add CANDEM vCAN 0 and then 1E0 colon 7FF. And then we can see that only CAN frame with arbitration ID X1E0 are displayed. And we can see that if I had a new option, which the delta between each frame, I can see that the periodicity of my frame. So every 400 milliseconds, a CAN frame using arbitration ID 1E0 is sent. And these CAN frames are always the same size. It's 7 bytes CAN frame. Okay. If I want to display a range of arbitration ID, for example, all the ID between X400 and X4FF, it's also easy with CANDEM. I just nudge you. I want 400, and my filtering will be 400 of the two last part of the registration ID has to be a wildcard, and then, well, the issue. No, sorry, I did a mistake. It's 7FF because I want to properly filter my form. And then I have only one CAN frame using arbitration ID between 400 and 4FF, X400 and X4FF, which is X421. Okay, so very easy. Okay. Play a little bit with this on your virtual machine, on your computer. If you have any questions using just CANDEM, very basic, very easy. I want to read that on the canvas, yeah, CANDEM, and adding some filtering and some option. Okay. Then we saw that just using CANDEM is not the most common way to find data, to identify data and what data are used for on the canvas. There is another command which is CAN sniffer, and CAN sniffer is very powerful using the -C option because it will highlight changing data and any new data between two CAN frame using the same arbitration ID will be highlighted by being colored in red. Okay. Also, using CAN sniffer, if a CAN frame is unmodified for a few seconds, it will be hidden on the output. So, if you have a very big output, and if you have a lot of data, a lot of CAN frame in your canvas, it will allow you to reduce the output you have to work with, and it's way better to identify the data you are looking for. Also, you can use some filtering using CAN sniffer. So CAN sniffer has an interactive control. So into the display, if you, for example, type plus X123 enter, it will display all the arbitration ID having all the CAN message having arbitration ID X123, for example. So if each mask has arbitration ID before, this allows you to show them again. And if you type minus X123 instead, it will do the opposite, and it will hide this arbitration ID from the output. You can also use the same kind of bit masking that you can have using CANDEV with using 6 digits input instead of 3-digit one. Okay, so let's have a look. I will use my CAN sniffer using -C command. Then we can debug. Okay, so I see that, for example, CAN frame using arbitration ID 2C5 just send the same data at all the time. So it has been wait a minute, sorry. Sorry. So we can see that all the constant data are hidden from the display. And then it's very useful because if I do some action on my car, for example, I get higher speed, I will see that the data will be also changing on my canvas. It will be not clear to you, but there is a speed because it reduces with the speed. And if I accelerate again, look for those 2 bytes, okay, using arbitration ID 1X1E0. When my speed goes up, I see those 2 bytes are increasing, okay? And this is very easy to identify it with CAN sniffer. As I said, if I want to mask 1E0, I will type on my terminal -1E0 enter, and then 1E0 disappear. If I want to display it back, I just have +1E0 enter, and then it's back. If I want to display all the data, all the CAN frame of my canvas, I just have +6 times 0 enter. Yep, I do. Yeah, I have an issue. Well. Okay, I have an issue, but it must be working. And it will display all the data. Okay, back to the PDF. So, okay, as I said, using CAN sniffer, if you want to find out which is the arbitration ID, which handle the John signal, it's very easy. So I'm going back to my terminal. Okay, and using the key left and right, okay, the arrow left and right, I can, when I press it, just press it and release it, it will, for example, trigger the left turning signal. And we can see almost instantly that on arbitration ID X421, the first byte is switching from 0 to 1. If I stop my blinkers, it stays to 0. Okay. Now I want to activate the right blinkers. And then the data changed and is 02 instead of 01. And it's quite logical because on the canvas, we have, on the CAN frame, sorry, we have up to 8 bytes of data, but each bit of the CAN frame could be affected to a specific information, a specific task. And for example, for blinker states, only 1 bit is sufficient and not a byte. So yeah, depending on the data that are using on a specific CAN frame, a bit or many bytes will be useful for the data the ECU as to read or as to send to other ECU. Okay. No, just a question for those who want to use the chat. A little question. Could you see a way of lighting up both sides of the turn signal at the same time? Okay. What would be the value that have to be sent on the CAN frame using arbitration ID X421 to light, like a warning, the left and the right blinkers? I don't have access to the chat, so I don't know if someone is writing something. Okay. Okay. So, for example, if I want to display both blinkers, it will be 01, X01, plus x02. So if the value there is x03, it will light the both indicators at the same time. Okay. Now we are able to read on the canvas. We want to send some data. Okay. And then there is another command, which is can_send, very logical name. Okay. When we want to use can_send, it's very easy. We type can_send, the bus we want to use, the arbitration ID, hashtag, and the data we want to send from 0 to 8 bytes if we are using a standard CAN network, and up to 64 bytes if we are using a CAN-FD network. Okay. So as I said, for example, I can send an empty frame in the canvas, typing this command. So I will send a CAN frame using arbitration ID x321, but with no data at all. And if I want to send, if I'm using a CAN-FD bus with a CAN-FD transceiver or using the virtual CAN bus, if I want to send CAN-FD frames, so up to 64 bytes of data, I have to use 2 hash. And then before the data, I have to set a flag, and just by default, that's the 0 flag, and it will be okay. And then I can send up to 64 bytes of data. Okay. So very easy. Now, as I said, we will open 2 terminals on our two terminals to have at the same time CAN-dump and the CAN-send output, and we will observe the results. We saw that our turn signals are using the arbitration ID 421, and the first byte of this arbitration of this CAN message handles the turn signals. Okay, back to our terminal. Okay, I will filter all the message using arbitration ID 421. So I have all the legacy message. I see that my right blinkers is still active, so I will trigger it off. Okay, so now I have my message using, okay, no transitional active. And I will send on my canvas, we can 0, arbitration ID 421, X, for example, to light the both blinkers. My first byte will have to be set at 03. Okay, so we saw that the blinkers, the indicators, are light up, but are just trigger off just after, because the way the ECU works, as I said, the CAN frame are sent periodically. So I will send my fake frame there, and it will be quickly erased by the regular frame of the ECU. So if I want, for example, to have my indicators lit all the time, I have to write many CAN frames quicker than the regular one. So I will get over there and then have a major effect on my car. Okay. For example, if we want to, we could use this kind of loop to, for example, make the transitional blink, or to have them light up at all the time. Okay. They will blip a few times, because if, for example, we send 10 times quicker than the real frame, time to time the ECU reads the real quick frame instead of our spoofed one and do the effect it has to do. But yeah, the quicker you are, the better the effect will be. Yep. If we want to send a periodic message on canvas, we have an alternative to the loop I just showed you. And there is a very cool command, which is CANGen. The bad thing about CANGen is they use uppercase options that are not regular with all the other CANutils commands. Yeah, that's a bit tricky. But for example, if I want to send a 4 byte of data using the data didbeef on my canvas every 100 milliseconds, using arbitration ID x123, this is the command. It will be CANGen minus upper I 123, upper L 4, so that the length of the data I want to send, upper D, the data I want to send, and minus case G, the timing in milliseconds between two frames, okay, on my bus. All these arguments there could be replaced by a I in minus or R. If you use the I, it will increment the data. So if I want to fuse the bus, I want to fuse some data, it will start from 0 to, for example, the 7FF, or there, if I have 8 bytes of data, it will be 8 times XFF. Yep. I can also use the error, and if I type error, it means it will be random data. It's very useful. For example, if you have, you get an ECU from a scrapyard and you plug it in, you pour it, and nothing's displayed on the canvas, that means the ECU needs to receive what we call the wake-up frame. And using CANgen and sending arbitrary stuff very quickly, you can trigger the CAN frame, find it very easily, and then you will know that you have to send this frame periodically, for example, every 100 milliseconds. Keep your canvas alive on this ECU, so it will be poured on and you can play with it and do many stuff with it. Okay, very important. Yes, that's just what I said about the I and R option, which is incremental or random values. Beware anyway, on every car, there is what we call the crash frame. It means when you are driving and you have an accident, the airbag control module will send a crash frame over the canvas, and this crash frame has one main effect. Is pour off, it shut off the engine. So the injection, all the gasoline are not sent to the motor to avoid any, to avoid that the car starts to burn. And also it unlocks all the doors. So any surrounding people or emergency could extract people from the wrecked car very easily. As we saw that the lower the arbitration ID, the higher priority the message will have. Such kind of frame will have a very low arbitration ID. So if you play with the real car, avoid doing a big fusing on arbitration ID below X300. If this is an arbitration ID that it exists on the canvas, you can try it. But if this is an arbitration ID you don't see on the canvas, it could be a crash frame. And triggering the crash frame could be very painful for you, because if you don't have access to a real diagnostic tool or to some specific knowledge, you won't be able to start your car again. That's something you don't want to have with your car. So you were using CANgen. It's good if you have ECU, some kind of ECU when you build a test bench, but yeah, take care. This kind of using the crash frame will be on, I said there is different kind of canvas on a car. There is a canvas which will handle all the body related stuff, like looking and looking the door and stuff like that. And there will always be a canvas that will handle all the motor related parts. And that this canvas will be the one connected to the UBD2 plug, if the UBD2 plug is not filtered by the gateway. So this kind of frame will be sent on the motor related canvas. So yeah, take care of it. If it's your infotainment unit network, you can fuse it as you want. You may not trigger any crash frame at all. So now using CANgen, we want to light the joint signal up and stay them lit all the time. Okay. It will be very easy. Just type CANgen, uppercase I.
Hey, Philippe, sorry to interrupt. There's a question on the Zoom chat. Is there a difference in brands, what they use for arbitration ID, or do they all use the same? For example, all the same bits for the turn signal?
No. Each CAN frame are manufacturer specific. If you are lucky, because it's when a manufacturer, tier one manufacturer, work with to design a car, they want to keep the stuff to an ECU. If you, for example, I rephrase. For a specific manufacturer, the same kind of ECU can be found in different model of a car. And they will have their own arbitration ID database. So for example, some manufacturer will use exactly the same arbitration ID for the same information on all their car. For others, it will be for range. Okay, for example, if I speak about Ford, the Focus, C-Max, Fiesta models are from the same range, so they will share the same arbitration ID database. But the arbitration ID database we will find on those models will not have the same effect on under the same information on other models of this brand. Okay, but arbitration ID are really brand manufacturer related. So, for example, the 421, if you find it on a I don't know, a Porsche, will not be available on a Renault or any other car, for example. Okay, it's the same about the crash frame. They are manufacturer specific. Some manufacturer will have the same crash frame for all their models, and other will use a specific arbitration ID for different kind of models. Any other question? Okay. So I want to lit my turn signal up all the time using CAN. So I set my arbitration ID. The length of my CAN data for the turn signal is 3 bytes long, and the data I want to is 03, and I will put some garbage FFFF. Okay, and I want to send it every 100 milliseconds on my bus, which is VCAN 0. Okay, so now what's happening? Okay, we see that our turn signal are almost all the time up, and time to time, the real CAN frame is received by the instrument cluster. So that's why the turn signal are switched off very, very quickly. Okay. So very easy to generate random stuff. Okay. If I want, for example, to generate random data, I just tap -R there, and the output will be okay. We see that there is random data that are stored on any CAN frame sent using CAN-gen. Okay. And you can play with this at home, but using some specific argument with CAN-gen, you can do some cool stuff when it comes to instrument cluster to light in a way some signals and stuff like that. Okay. Now CAN dump has another cool option, which is the recording. If you want to do some post analysis on your canvas, or you say if later we want to replay data on canvas, using the option -L, we'll record on a log file all the data that are going through the canvas. Okay. It's also possible to filter the data you want to log if you want to reduce the output of your log. Okay. Very easy. So if we do it, for example, CAN dump -L VCAN 0, we will start to log all the data going into the canvas. The fact is you cannot choose the name of the log. It will be created automatically. It will be the date and the timestamp of the time you grab the command. Okay. If we look at the content of the log, it will be the timestamp when the frame was received, the canvas on which the frame was received, and then you will recognize the CAN-send format, which is arbitration ID, hash, and all the data, okay, in bytes. As you can understand, it's if you have multiple buses, you can, for example, if I have a VCAN 1, another virtual bus, which is VCAN 1, I can record many buses at the same time. That's very cool, okay? I have another command, which is CAN player, which allows me to replay a log on my CAN bus, okay, on my virtual CAN or on my real CAN bus. The command are here again using some uppercase, which is a pain in the ass. So the command, standard command is CAN player, upper I, the name of your log, -L, the number of time you want to replay the log, and then if you want to, you will say on the log, this CAN interface will be transmitted on my CAN interface, for example, there VCAN 0. If you don't put this information by default, CAN player will try to send the data on the canvas. It has been recorded. Okay, so it's optional. It's very easy. And what is very powerful using CAN dump and CAN player is when you are working on a car. when you are working on a car and you want to know if there is an active command on your canvas, you just record the bus, you do some commands, you replay it, and if you see some effects, you know there is a command frame that is available on this bus. Okay. If nothing happened, for example, you want to learn how to lock and unlock the door on your car, you will be connected to the main canvas from your OBD2 plug, for example. You lock and unlock the car, you play with the key fob, and then you replay all your log, and nothing's happened. It can mean two things. The first one, you're not on the good canvas, which handles the door lock. The other one, there is some security on the can frame, for example, a counter, stuff like that, that block you from replaying some data. Okay. Just the last thing about recording a canvas, Wireshark is able to record can data. If you are on Linux and you are using Wireshark, it will use your CAN interface as a standard interface, and you can display and record all the data onto your canvas. And you can also apply some protocol decoding for advanced protocols. So reading all the data is way easier. Okay. So if we want to replay some data using CAN Data Player, for example, as I just said, are we able to lock and unlock the door on our virtual car? So for example, I'm on my car, okay, with the key Q and E, I can, for example, Q, open the left door or close it, okay. I will remove my log, okay. And then I will log my canvas. I will open and close my drawers. Okay. And using Control-C, I will kill my dump. Now using CAN Player, uppercase I, my log file, I will repeat it all of the time. I will do a loop, an infinite loop, and then here we go. And now we must see that the drawer locks and unlocks. But you see, it's very quick. Why? Because there again, CAN Player is fighting with the real frame. So if the real frame I send very frequently, the effect will be very short. But we just saw there that there is an effect. I am able to lock and unlock the door using CAN Player and CAN dump. So I'm on the good canvas to do such stuff. And it exists a CAN frame, which is a command to say, okay, lock or unlock the door. Now I want to find out what the CAN frame to lock and unlock the door is. And it's very easy because I can use the split command. Okay. Split command, my CAN is just a text file. Okay. So for example, here I log. I have logged only 100 frames, okay, which is very few, but on a real car, you will have thousands of frames, okay. So if I just for example, split by half my CAN log and replay the first half and then the second, just replay the first half. If something happens, I know that my command, my frame, commanding the unlocking of the door is present on this part of my log. If it's not, I will replay the second part. And if something's happened, I know that the command is present there. If nothing's happened, it's because maybe the CAN data used are much more complicated with the pattern and stuff like that. Then I will split again in half the active part of the log, and then going so and so, I will reduce from thousands of lines to maybe up to 5 to 10 lines, and then finding out which is the active frame, which is a good arbitration ID, CAN data to lock and unlock my door, will be very, very easy. Okay. I will skip it because we will have time to get through all these workshops. But for example, if I want to lock the door and using the CAN split command, the split command with CAN Player, sorry, I will find out which is the byte which will lock and unlock the door. And for example, there I can try to unlock the trunk of my car, okay, which is not something I have access to using only the keys there. Okay. What is very important when you play with a CAN frame, that not all CAN messages have a physical effect. Remember that the normal behavior of an ECU is it's read data from sensor and then control actuators and send this information to other ECU using different kind of bus, like the CAN bus. Okay, different kind of network, sorry, like the CAN bus. For example, if I want to switch the light on and off, okay, I'm on my car, I'm using my switch to set the light on and off, and on my instrument cluster, the display will switch to light on and off. So I will record the CAN frame, replay it, and then I can be able to trigger this display on my instrument cluster. But if I get outside and look at my car, my lights won't light up, okay? Because this is an information that is sent on the CAN bus. It's not a command. And why it has no effect? Because maybe the light switch is directly wired to the ECU. And this is the ECU, for example, the body control module, who reads the state of the switch and say, okay, the lights are on. As it's the body control module handle also the light, it will say, okay, I have direct input on my sensor saying, okay, light the light up, okay. And then it will trigger one of its relay and switch the actuators to light the light up, okay. And the data we will find on the CAN bus is only information, it's not command. And for example, if I want to light the light, okay, or up the light, maybe there is another ECU, which could be the front camera using a photosensor. And if the photosensor value is too low, send the data saying, okay, there is no much surrounding light, so we have to use our driving light. And when the BCM receives this message, it will trigger the road light, okay? That's something that you can try with the virtual car, okay? It's using the arbitration ID. I will filter it right now. Okay. If I switch there in night mode, okay, the first byte switch, okay, this is 0, but this is an information. It just will trigger this one. If I, for example, do a CAN jam very quickly on a 2 bytes, sending only 0, sorry, every 5 milliseconds. What's happening? Well, it's not working there, but normally this one will shut off, but we saw that the lights are still on. And you have to find the arbitration ID for the front camera module, which will tell, okay, this is the external light, the luminosity of my surrounding, and using this information, the body control module will trigger the light on and off. Okay? Very important. Always keep in mind on CAN bus to have information on that control. Two different things. Okay. And for example, if I do this command, so I'm still at night. I stop my CAN gen, I use this one, and then we saw that we are on the arbitration X5D1. This is the surrounding light information. And when we tell our BCM that, okay, there is light, it's the day, so you can shut the light off, then we have an effect and we are driving by night and we don't have any light at all. And this is dangerous, okay? So we saw two differences between the indicators and the real status, the control of the light. Okay. It's almost done about the CAN bus. Very quickly, the main flows attacks that are available on CAN bus. We just saw that the CAN bus is very easy to replay data on the CAN bus. So the CAN bus is very vulnerable about any kind of replay attacks. It's very easy to get data from CAN bus, to dump the data, to replay it, and to have effect, to have some control on some ECUs. Although the arbitration ID system use does not authenticate the sender. So if you honestly received the arbitration ID is listening for, waiting for, it does not mean that that's the real ECU that has to send such arbitration ID that sends the message. There is no control at all on this. So it's also very easy to natively spoof an ECU. Okay. Using the error frames, as we saw at the beginning, can generate a deny of service on a car with a bus of attack. So if I manage to send many error frames on my bus, as each time an ECU send a data and receive an error frame, it will increase this transmit error counter, and when this counter gets over 255, we will switch off the bus for a certain amount of time, a few milliseconds, then get back. If we have a loop doing sending such error frame, I can manage to disconnect all my ECU on my car. And it's very easy to generate a new car. Go to your OBD2 plug and just short wire the CAN high and CAN low pin. You won't damage anything. It's just as you will have a constant data which is not compatible with the bit stuffing part of the protocol, it will generate ECU, will show error, and each ECU will increment their transmit error counter each time they transmit data, and will switch to base off. And you will see on your instrument cluster, for example, that everything will turn off. You will have no information about it. You may have control for every sensor and actuators that are directly wired to the ECU, for example, the BCM. You will still be able to lock and lock your car or turn the lights on and off, but you will not have any feedback, any display on the instrument cluster, for example. Or if you have, I don't know, you will not know the speed of your car because the ABS ECU will not be able to send data on the CAN bus. So yeah, very easy to do some deny of service on the CAN bus. And also there is no native encryption. It's very difficult to encrypt 8 bytes of data. If when you have just 8 bytes of data, it's very difficult to do some encryption. And it means that if you have to send some privacy related or critical data on the CAN bus, beware when you do so. You have to add your own protection. For example, I did a talk years ago showing that you can bypass two-factor authentication of access to the car, because on this model, when you pair your phone over Bluetooth and you read the text message on your car, the text message was sent in clear on the canvas. And so if an attacker has a way to put an implant on your car, you can have access to all your private or your text message. If there is also technique, so they can request text message from your phone and block the display on the car, so it will jump all the text message from the phone. That's not something you want to, because this is privacy related. Okay, so be aware. These are really the main flaws on a canvas. There is techniques to protect them using mostly the gateway. So gateway is the shield you will have on all the canvas and on your car, because it's under all the security for this whole bus, which is the canvas. Okay. A little bonus, if you want to, it's just about the OBD2 protocol. We saw that we speak a lot about the CAN, okay, the CAN bus. But a bit of history, car and ECU need to be diagnosed over the time to be repaired, to be properly set. And in 1968, Volkswagen introduced the first onboard diagnostic computer. Okay. From there was various diagnostic protocols that were developed, and the most recent one allows you to fully reprogram or reflash an ECU. Okay. Using specific diagnostic protocol, you can generate specific behavior that are designed to be only used during development or at a mechanic workshop purpose. But if you do it on the ride, when the car is driving, you can generate non-allowed or non-synced state that could be very useful when you are doing an assessment. Okay. But we will not get into this. We will just speak about the OBD2 protocols. if we adapt the OSI model for the automotive protocols, we saw that our network layer, physical layer and network layer is a canvas. And over this layer, we will have a transport layer with the ISO-TP protocol. And over there, the application layer will have the OBD2 protocol. The UDS one is a much more recent one with much more capabilities, but it's out of the scope of this workshop because it will need one day, full day to get into this protocol. Okay. But you can have some fun just using the OBD2 protocol. First of all, we will quickly speak about the ISO-TP protocol because it's the one that transports OBD2 data. We saw that on the canvas, we are limited to send, so on the legacy canvas, we are limited to send 8 bytes of data on the standard canvas. Using the ISO-TP protocol, we can send up to 4 kilobytes of data, which is better, and that's the way we can use, for example, as we have more data, we can send new firmware and stuff like that. So the ISO-TP, which means TP for transport protocol, segments the message you want to send into multiple frames on the canvas. And on this, if you read your canvas, you dump the data. For example, when next time you bring your car to a mechanic workshop, you manage to dump all the data when they plug through the diagnostic tool. You may see that there is some specific frame that are ISO-TP frame. And ISO-TP can be identified just using the first frame, which is the first byte, which is very important. And on the first bytes, the two nibbles, the high and the low one, have a specification. Okay, so the high nibbles, on the first byte, will tell you what kind of frame it is. It could be if the value is 0, it will be a single frame. But if we want to send more data, it will be 1, saying, okay, this is my first frame, and there will be data added to this one. And we will wait to a flow control frame, which will start with on the first byte, the enable will be 3. And then we will have many frames, starting with a 2, which means consecutive frame. Okay. So, as our first byte is used for which used to define the kind of frame we have in ISO-TP, we are left with only 7 bytes of data. Okay. Another important thing about ISO-TP is that most of the time there will be a padding. So, for example, as my I nibble on my first byte, it's 0. It means it's a single frame. And then the lower nibble on my first byte will be the length of my payload. So it means there is 2 bytes of payload. So my payload will be this. But most of the time, almost any manufacturer will have a panning, which will be 00 or AA or A0. It's manufacturer specific. Okay. So if I see something like that, it could be an ISO-TP data, but maybe not. It depends. Okay. And then, as it is over my ISO-TP protocol, I will send an OBD2 message. And OBD2 messages are very basic. They are made of 2 things. It's user services and a parameter ID, the PID, to request data from the ECU. If you type OBD2 protocol on Wikipedia, you will have a list of all the services and parameter ID that are available. And using those services and parameter ID, you can read data from your car, mostly that are for motor engine related. Okay. So, for example, if I want to, if it is enabled, because all the PID and services are not available on the car, but for example, the PID X2F is the fuel level, and it is used on service 01. So if I want to read the fuel level on my powertrain control module, which will be using the arbitration ID 7E0, okay, I just send this command. I have to send a 2-byte command, so it will be a single frame. I enable 0. Low nibble will be 2, and then this is my services 01, okay. And then my PID, which is 2F, and I have to add padding. And what is great when you are using ISOTP protocol, that's not ISOTP, sorry, but OBD2 and UDS. That's those protocols are verbose, okay, and they have to respect a specific pattern to reply, okay. And so if my request is correct, first, when I request an arbitration ID, the reply normally has to be with the requested arbitration ID plus 8. So I will have a reply on X7E8. Okay. Normally, X7E0 is on all the car. You will have your providing control module which will reply to this arbitration ID. For all other ECU, the arbitration ID used will be manufacturer specific, but most of the time on the range X70 to X7FF. Okay. And if the request I made is positive, then it will reply with the request services plus X40. So yes, as it's plus X40, it's a positive response. It will tell me the PID I requested, and there I will have the data requested. So there I requested for the current fuel level, and my current fuel level is X32. So I don't remember, it's something about 80%. Okay. If the service I requested is not available for any reason, I will have a negative response. We'll start with X7F. Then I will have the service that is for the one I will get the negative response, and I will have a negative response code. Okay, and you will also find the list of all those negative response code. And what is cool is regarding this negative response, you will know why you cannot access to this service. It could be many reasons, and just reading the negative response code will tell you why you can't get access to this one. So we're a bit short there, but if you want to, you can play with the virtual car to request using the OBD2 command to request the fuel level. Okay. So just going back to my terminal, I will filter all the data going from X700 to X7FF. Okay, and there I just requested using the OBD2 protocol my fuel level, and my fuel level is currently X49. You have to do the conversion, but there, if you look, I have an issue, but it will be correct regarding the current fuel level on my virtual car. Okay. The last thing to finish this webinar, this workshop, sorry, is we saw that using ISOTP, we can send up to 4 kilobytes of data. Okay. And that's where the first byte of the ISOTP frame is important. We just look at the single frame type. But if we have much more data, the high nibble of the first byte will be a 1, which means it's the first frame. So it's the start of all the data I have to send. And then the low nibble and the second byte will be the length of the data that will be sent. So there it will be X14. So that means it's 20 bytes of data that are sent. Then I will, for example, there I request an OBD2 command which for service X09 and PID X02, which is the VIN, the vehicle identification number. Each vehicle has a vehicle identification number. It's its own serial, if you want to. It's 17 characters, which is very specific. Also look for vehicle identification number on Internet, Wikipedia, and so on, and we will have the detail on all this VIN are designed, and it allows you to know the manufacturer, the model on which plant it has been manufactured, the kind of engine, stuff like that. Okay. So I will have my positive response, which is services plus X40, then the requested PID, and it starts to be my data. When an ECU reply with an ISOTP frame, it will wait, when it sends a first frame, it will wait for a flow control frame, this kind of frame, which will start with a sweep. Okay. If you don't send any flow control frame, the transmission will stop. if the flow control frame is not sent within a specific interval, if you send it too late, what's happening there? I return the VIN number using a bit2 protocol. This is my first frame. There I send my flow control frame telling, okay, send all the data. You don't need to have any more control, and send all the new frame with a delta of 10 milliseconds. And then I will have all my data. We saw that the high nibble of the first byte will be 2, which means consecutive frame. And the low nibble will be incremented from 1 to F. And when it reaches F, it will revert back to 0 and then increment again. And then there, for the 7 remaining bytes, I will have my data. And once I've reached the length of my isotp frame, I will have padding. Okay. If I want to read an isotp frame automatically using canutils, I have the last command I want to show you, which is isotp regv. Using isotp regv, you will tell, okay, this is my sending arbitration ID. The destination arbitration ID, so we saw that we request the data using arbitration ID 7x7E0. The reply is sent using x7E8. So we specify those 2 parameters. We say, okay, there is a padding used, and the padding on the sending part and receiving part is 0 on my bus. And when we type this command, isotp regv will wait for any incoming first frame. And when it saw the first frame, it will automatically send the flow control and grab and show you all the bytes of the data received. Okay. So this is the last hands-on. So to request, and it will work on a car if you have a CAN adapter, I will need 3 terminal windows. Okay. Oh, well, I will do it with G. So, for example, I will request service 09PID02, which is the VIN number, and there we can see that I have my first frame. As I don't send any flow control frame at all, I don't have the remaining data. Okay. So what I have to do is to go this way. I will type isotp regv. Okay. So the sending will be on 7x7E0. Destination is 7E8. I have a padding of 00 and vcan 0. Okay. So isotp regv is just listening onto the CAN bus. And this time I will send my request again. And we can see now that isotp regv send the flow control frame, and we get access to all the continuous frame without padding, because we reach the amount of data sent. And there we will have the VIN of our vehicle. If I, for example, I pipe it using XXG minus here, well, if I don't, okay. The output of XXZ is truncated because it missed 2 digits, two characters, but this is the start of my VIN, of my virtual car. Okay. So it has been very quick, but we also see advanced protocol on the CAN bus using the OBD2 protocol and the ISOTP protocol. Okay. It's almost done about the CAN bus. You have seen, or you can use canutil to play with the CAN bus, but there exists some alternative, mostly using Python. If you want to, there is a Python library which is called Python CAN, which allows you to read and write on the canvas. It's very useful when you go into more advanced protocol, when you have to do some security access requests, when you have to compute some key and stuff like that. It will be easier to create your tools to automate some research or attack on the canvas. But I also highly recommend using Scapy, which is also something that's run on Python with the very great work of Niels and Enrico, which managed to create some automotive contribution that's under almost all the main automotive protocols like CAN, UDS, USOTP, XCP, and all the automotive Ethernet related like DoAP, SOMAP. You can read the doc. And if you want to go to have some basics on Scapy, Guillaume will handle a free workshop for Wing Zero on June 13th, so in 3 days. So go there and register now because it's free, and when it's free, it's better. Yes, and I hope you have enjoyed this workshop. Working with the canvas, this is cool, but when we do automotive security, the canvas is not the only thing. So if you want to go deeper into cracking, come to the training at Ring Zero this August in Vegas. You will play with what we call the tiny ECU, which simulates hardware simulation of a real car. We also have the car in a box, which is a real car with patch in a case. So you can also play with the ECU to see what's happening on a real car. We'll get into how we can dump data from ECU, the firmware, how we can reverse it, explore some real case scenario, get into more advanced protocol, and also have fun with all the infotainment, because very good secrets you can get from infotainment units. Play with there you will have a key fob, and you will also get your CAN adapter. So when you leave the training, you can play with your car or someone you don't like to, because if you break it, it's better if it's not your car. So yeah, that's it. I don't know if you have any questions. I'm here to reply to it, and I hope you have enjoyed this quick workshop about the canvas.
Folks, if you have any questions for Philippe, please pop them into the Zoom chat, and we'll read them out and answer them for you.
Okay, good. Thanks, Omar. Okay. Anyway, if you have the virtual machine, you can replay with it all the small hands-on I have shown to you. On the virtual machine, you also have Scapy, you have Python CAN. So if you want to get into using Python with the power, that's the way to start. And if you want to get deeper, as I said, come to this option. Yeah, that's it. It works. You can also, using this option, display the output in ASCII. So it's better to read the VIN of the car.
Any other questions, folks, that you may have for the workshop or even for the training? Be happy to answer. There's one.
Yeah. So is attack working in private network, or is there any jump tool? The fact is, the working with the canvas, is at the end. It's when you can start to exploit the car you made your attack. You have to find a way to get into the car. That's another part. When it comes to automotive, as I said, each ECU can be seen as an embedded device. So you have to look for vulnerability into your embedded device or the attack surface. If you get access to an ECU which have any Bluetooth or Wi-Fi communication, you manage to get access to it through this communication, maybe you will find a way to send some kind of command, and then that's the way you can generate effect and attack on the car. As I said also, the other way is that manufacturers are only afraid about remote attack. But on certain case, for example, if you are a blue team for a big company, okay, you work for blue team for a big company, and on your company, there is a pool of vehicles that are available for the C-suite, for example. A bad person, if they have access to the car, they can plant an implant and get access to some data for, as I said. Maybe they will find a way to read text message from the phone or some stuff. So even the local and private attack has to be secure depending on the context you are working on. Yeah. But there also finding dumps of CAN data is not something very easy. You can find on the internet. It's not people don't send a lot of CAN dump over the internet. They will just say, okay, I have an issue with my car on specific forums, and other CAN guys will say, okay, use such diagnostic tool on very higher level, user level tools. There is also some tools, professional tools that you can use that will give you a nice UI to read data from the CAN bus, from the 2IP protocol and stuff like that, for example. But it's very cool that using CAN utils or Python, you can craft your own tool and manage your attack. Detection is here available. What do you mean, Mirko? Using higher like verbal code, it's very easy to craft a scanner that will detect ECU. Otherwise, no, there is no detection ECU that are available. If you mean anyway, ECUs that act as an intrusion defense system, an IDS, you may have one that could be the gateway if it is well designed to detect some kind of attack and send an alert to the driver, to the backend, so the manufacturer knows that an attack is going on their car. Yeah, I don't know, Mirko, if I reply correctly to a question. Okay, yes, IDS. It will be the task of the gateway. The gateway is really the main ECU, which is coming to security of the network, because it's what it has to do. And then there is no standard IDS that exists. There is many study and paper about how we can detect attack, how we can bypass this detection and stuff like that. If you have some time to spend to read all those papers, they are very interesting, but there are many papers. But yes, manufacturers are including the capabilities of the gateway, and they are thinking about getting better and better IDS. Mostly with connected ECU, because the attack came from the outside and not only the onboard network of the car. You're welcome.
Hey, Philippe, I had one last question personally. Do you know what type of firmware do these ECU runs? I mean, it's sure it's bare metal, but is it like?
It brings me to one other thing I want to say to Mirko. It's on the automotive industry, everything is cost related. So they will not spend a lot of money on the ECU. If the ECU can be cheaper, they will try to do it, because the car will be cheaper to buy, and you don't want to spend 1,000 or 2,000 euros or more to get your car, because it is more secure in the cybersecurity point of view. I mean. So for the most basic ECU, you will have some very, very basic ECU. We will use very basic microcontroller, and so the firmware will be bare metal. And also the microcontroller used will be most of the time automotive specific. So you will find NXP, you will find UNSAS, you will find I don't have them in mind, but very specific microchip, for example, microcontrollers, and the reversing part could be tricky on them, because there is no that is no microcontroller and instruction sets that are natively support most of the reverse engineering tool. But for the most advanced ECU, like a telematic control unit, a gateway, you will have a system on chip, and on the system on chip, you may have a Linux standard OS, hypervised or not, which is running on it. So you will have, there is no on a car. Each ECU is an embedded device, and on each ECU you will have maybe one or many firmware, microcontroller, or one and a SOC or not. So getting access to all the firmware and reversing them is very time consuming, because they are all almost different. Because if you have one, for example, microchip, microcontroller on the ECU, that doesn't mean that all the microcontroller on your car will be a microchip. For example, we will have an XP, we will have an SAS, many others. And sadly, ARM microcontroller are not the most common one you will find in a car. Yeah, that's sad.
Thanks, Philippe. So, folks, we will, let's say, Philippe, thank you very much for the workshop.
Welcome.